Now there could be a problem like this. This is the compound and you have been asked to draw position isomers of this compound. Now, although the topic is rudimentary, but this could be a little problematic for you initially to think of what can be the positional isomer. You try drawing as many positional isomers as you can. Remember the basic definition, the basic carbon skeleton will remain the same and the position of either functional group or pi bond or substituents will differ, will vary, will change. Now here you have to keep the basic carbon skeleton same. This will remain same. Only this chlorine will hover around to different positions and correspondingly you will get different isomers. So if you bring chlorine here, then this is one of the positional isomer because the position of chlorine has changed. Similarly, if you bring chlorine to this position, you have another positional isomer. Similarly to this position and this position will fetch you two more positional isomers. If you go to this position, this will be similar to this position because of symmetry. If you go to this position, it will be similar to this position. So altogether 1, 2, 3, 4 and 5. There will be 5 positional isomers to this given compound, counting this given compound. Okay, let's do a final problem on this. Question is like this. Positional isomerism will be exhibited by which of the following compounds? Your options are position number 1, dichlorobenzene, number 2, xylene. Xylene, remember we did a moment back. Toluene. Now toluene, I don't know, you may be knowing, you may not be knowing. Cresol, you may be knowing, you may not be knowing. Xylene you got to know because I have told you already. And dichlorobenzene will not be a problem for you. You have a benzene and you have 2 chlorine on this. It could be at ortho position with respect to each other, it could be at meta position with respect to each other, it could be at para position with respect to each other. So of course it's going to have position isomerism. The positions are changing of substituent on benzene. So the option number 1 surely is going to give you positional isomerism. Xylene, we have seen orthoxylene, metaxylene, paraxylene. Xylene is going to give you positional isomerism. Toluene. Now toluene is a compound on which methyl group sits at the top of benzene ring. This is toluene. You don't have 2 groups to be interchanged with the positions. You have a hydrogen at all these positions and there's a symmetry here. You change this methyl to any other position. This is not that will not give you any different compound. Just rotate this compound with 60 degree, you're going to get this. So this is identical. So toluene is not going to give you positional isomerism. Just by looking at the structure you can identify. Cresol. In toluene, if you have an hydroxy group, then that is cresol. What would be this? Orthocresol, metacresol or paracresol? They are at ortho position with respect to each other. So this is orthocresol. They could be at meta position with respect to each other. This will be metacresol, similarly paracresol. So yes, this is going to give you position isomerism. Fine. This is what they can ask when positional isomerism. Position isomerism is done. Next we move on to another kind of structural isomerism. This will be called as functional isomerism. Functional isomerism, as the name suggests, the first of all isomerism, so molecular formula got to be same. Now functional isomerism will have same molecular formula, but they'll have different functional group. For example, suppose a molecular formula is given as C3H6O. Now this can be acetone, C3H6O. This is a ketone. This can be a aldehyde as well. This can be propanol, C3H6O. This is also having, they have same molecular formula, but the functional group is different. Functional group here is ketone, and functional group here is aldehyde. So they are functional isomer. That's the definition of functional isomerism. Functional isomerism. Simple. Now, question is, you get me the functional isomers of ethanol, C2H5OH. Now get your acts together and try and find the functional isomers of ethanol. Similarly, you try and find the functional isomer of 1,3-butadiene. And you also try and find the functional isomers of ethane nitrile. And you should also go ahead and find the functional isomers of benzyl alcohol. Try these four, work them out, try and find the functional isomers of all four of them. You will have a good practice of drawing the functional isomers. And anyway, we are going to discuss the answer, but it would be better if you do it on your own. Okay. Now functional isomer, you have to think of different functional group. The given compound is alcohol, so you have to get a different functional group using the atoms you have. Then you have to think of how many functional groups you know and how many functional groups actually have one oxygen. This alcohol have one oxygen, right? So you have to think of another functional group which actually will have one oxygen. Nitro group cannot be it have nitrogen, 2 oxygen. Acidic group can't be it has 2 oxygen. Ester group can't be it has 2 oxygen. Which more functional group do you know? You know amine, nitrogen is required, it can't be this. Which more functional group do you know? You know ketone, but it has a degree of unsaturation, double bond. This does not have a degree of unsaturation. If you try drawing a aldehyde, the molecular formula will not match. This is C2H4, you have been given C2H5OH, 6 hydrogen, it has 4 hydrogen, because of degree of unsaturation of double bond. So this can't be it, aldehyde can't be it. Which functional group do you know? You know a functional group which is called ether, where you don't have a degree of unsaturation and all it requires is one oxygen. So if you can make an ether out of this alcohol, the functional group will change, and that will be called as functional isomerism. So one of the possible, or the only possible, functional isomer of ethanol is this ether, dimethyl ether. Fine. Now you have 1,3-butadiene. 1,3-butadiene looks like this. If you, without hydrogen it looks like this. With hydrogen it will look like something else, but without hydrogen it looks like this. It is 1,3-butadiene. You have to draw functional isomerism. The functional group here is alkene, and you have to get a different functional group. Then what can you get? The only thing you can get is alkyne. From alkene you can get alkyne. 2 pi bond, here you have 2 pi bond. Molecular formula has to be same, because degree of unsaturation is 2, here also degree of unsaturation is 2, number of carbon are same, number of hydrogen is bound to be same. Functional group, molecular formula same, functional group different, functional isomers. Fine. Ethane nitrile. Now this cyanide group is called nitrile. Now the name, you can name it as cyanomethane, you can name it as ethane nitrile. If you have studied the nomenclature of cyanide, you will know how to name it. If you don't know it from now. This is ethane nitrile. Now you have to get a different functional group. How are you going to get different functional group? This is cyanide. Which other functional group can you get where you have nitrogen? Nitrogen is there in nitro group, but nitro group requires oxygen. You can't get nitro group. Nitrogen is there in amine, and it requires hydrogen. Hydrogen are available. Hydrogen can be given. So you can get an amine out of this. How you can get an amine out of this is like this.